In the last video, we introduced the involution on the L1 of G. So now we have the L1 of G has a Banach star algebra structure. So in this video, I'm just going to talk a little bit more on the properties of the L1 of G as a Banach algebra. Right. The first thing I want to talk about is that the L1 of G is abelian. Actually, if and only if the G itself is abelian. Okay, so let's take a look at the proof. That's on one direction. So let's assume that G is abelian. So if G is abelian, then when we introduce the modular function, we saw that for abelian groups, the modular function is always equal to 1, okay, or delta x equals to 1 for all x in G. Okay, so in other words, the abelian groups are all unimodular. One way of saying this unimodular is essentially just saying if you want to integrate, say, h of x, the mu of x, can use the left Harmonic measure, then it's the same as integrating hx inverse d mu of x. Okay, so you can pretend they're the same thing. Right, so now, given that G is abelian, I want to show L1 is abelian. Here, the abelian just needs to mean abelian under the multiplication on the L1 of G is the convolution. So let's start by considering two L1 function f and g, and let's convolute them. Okay, so their convolution by definition. This is equal to, let's use the formula, let's say f of y and then g of y inverse of x. Let me just use dy instead of d mu of y when the context is clear. Okay, so whenever I say dy, it just means the Harmonic measure. All right, so now I can now use that the modular function is equal to 1, so I can integrate instead of dy, let's replace all the fy to the fy inverse. So this one becomes the integral of f of y inverse, and then you have a g of the y inverse becomes y. Okay, so this is yx dy. And because your group is abelian, you can replace this yx by xy. So let's just pretend this is an xy instead. Okay, so here let's replace it by xy. So here is by abelian actually. And now let's use some left translation. So I want to move the g to the front. Okay, so actually you don't even need to do that. This is, if you reverse the order, this is the integral of g of xy, f of y inverse dy, and based on the two formula we had for the convolution, this is essentially the same as g convolute with f evaluate x. Okay, so this finished to prove that the backward direction. The forward direction is slightly more complicated. So suppose I know the L1 of G is abelian. So it just means for every two function f and g inside L1 of G, their convolute, the convolution f and g minus g convolute with f. Let's evaluate at any point x, I will receive a 0. Okay, so that's basically what I mean by abelian. So let's write out the integral formula. So the first one I can write as integral of f of xy, g of y inverse. And the second I can write it as g of y and f of y inverse of x. Okay, so that's basically just by definition. So dx again is by the integrate respect to the Lagrange measure. All right, so you want to group them together, okay? So you always try to make them into something, multiply something else, and you notice there is a gy here and then gy inverse here. So you can do basically do the same thing again. So you want to replace the first integral, the y inverse in the first integral by y. Okay, so here we don't know this g is abelian or unimodular yet. So when we want to reverse it, we need to add a modular function. Okay, so if I want to integrate the fxy g of y inverse dy, I can rewrite this, replace all the y by y inverse. So I have x y inverse, and then I have a g of y, and then I need to compensate by multiplying the modular function of y inverse. And then I say d mu of y, okay, or just say dy. So let's just replace the first integral and we'll keep the second one the same. So now we integrate this whole thing and we have a g of y here and then I have a g of y there. So I can group them to have a g of y multiplied by what I have is f of x y inverse, the modular at y inverse, and then minus a f of y inverse x, the whole thing dx, okay? All right, I should say dy here, okay? This should be a dy. All right, so because here the f and g, they are just random, okay? So they can be any L1 function. So if you integrate L1 function g of y against any of the things in here, and you still get a 0. So this is for all g. So it just means that you're integrating something against 0. Okay, so that's kind of clear. All right, so this implies the following. So I have the f of x, y inverse delta of y inverse. That's going to be equal to the f of x. Here I have y inverse x. Okay, that's for all the x and y. Okay, so this is what we have. All right. Now, because this holds for all the x and y, so let's just pick some particular x. Let's say so for x equals to the identity, then what it tells us is the following. So I have f of y inverse delta y inverse, and that should be equals to the f of y inverse. Okay, so here the x is the identity. So basically, this as long as the f of y is non-zero, then I can have the delta of y inverse has to be 0. Because I know for any y, there has to have some L1 function f that makes f1 non-zero. Okay, so in other words, this delta y has to be equal to 1 for all y. Okay, so let's say for every y inside G, there exists some f inside L1 of G, so that the f of y inverse is non-zero. Okay, so that basically implies the delta for this particular f. I run this formula, I get delta y inverse has to be equal to 1 for all y. In other words, this delta has to be equals to 1. Okay, so in other words, your group is going to be unimodular. But if your group is unimodular, then if I look back to this formula, so now we know that delta is equal to 1. So I have the f of x, y inverse. Let's just replace the y inverse by y. Then I have f of xy is equal to f of yx, okay? And this is for all x and y again. And because if you have xy and yx are two different points, then you can use something like a Eurozone's lemma to find an L1 function that's supported on a small neighborhood on one and is equal to 0 on the other. So it's going to, your function will see the difference between these 2 points. Okay, and now because xy and yx cannot be differed by any function, so that just implies xy has to be equal to yx. That's for all xy, so your G is abelian. Okay, so let's finish the proof. All right, so we basically show that the L1 function under this convolution is abelian if and only if your group is abelian. All right. So the next thing I want to talk more about is about this the unit of an L1 function. Okay, so in the Banach algebra, so a unit is essentially just a unit you expect in the group. Okay, so you multiply on the left and right to the same thing. All right, so in fact, your the L1 of G is rarely a unital algebra. Okay, so here's the proposition. So it's actually only unital when it's discrete. Okay, so if let's say G is discrete, then I have this the L1 of G is going to be unital. All right. So why is unital? Well, let's just let me tell you what the unit is. The unit essentially is the chi of E. Okay, so the chi E inside the L1 of G is given by this function, basically the characteristic function of the identity. So that's equals to 1 if x equals to identity and 0 otherwise. Okay, so you actually have chi E if you convolute with any other function f. that's the same as you convolute on the other way, and that's equals to your function, okay? So this is for all f inside the L1 space, all right? So let's prove this fact. Well, first of all, if you're because your G is discrete, then this chi-e, because it's discrete, then the singleton point is closed and open. So the chi-e itself is indeed inside the L1 G, and it's a non-zero function. Okay, because when you're discrete, the left part measure, you can just put the counting measure, for example. All right, so if you want to do the convolution, so let's consider what's the chi-e convolute with f, evaluate at a point x. Okay, so this is essentially equals to the integral of this constant 1, or not constant 1, chi-e at say y, and you put the function f at y inverse x, and then you do the dy. Again, dy is the left part measure. And because you can, let's just pretend that the dy is just the counting measure. All right, so this chi-e of y is only equals to 1 when y is equals to the identity. Okay, so this whole thing, you can just write it as another way of writing this is just summation over all the y of the chi-e of y f of y inverse x, and only when y is equal to the identity, you get a non-zero value, which is 1. And then so when f is the identity, when y is the identity, you're basically adding up the f of x. Okay, so when you convolute on the left, you get f of x. Similar thing happens when you convolute on the right. Okay, so you can see that this chi-e is the unit. Okay, and in fact, this is an if and only if. Okay, so a fact. Okay, so if G is discrete, that's if and only if your L1 of G is unital. Okay, so if you want to have a unit, that's basically the same thing as saying your G has to be discrete.